Hi everyone, welcome back to my tutorials. I like to do a video where I solve three geometry problems that have appeared on math competitions for juniors and seniors in high school. So these are, I've taken these from medium to harder problems on the competition. So let's take a look at this first problem. We're given a square of perimeter 4. And we want to find the perimeter of the equilateral triangle. So if the square has perimeter 4, its side is length 1. So we know since triangle AEG is equilateral, its angles are going to be congruent, right? And since BDFG, so this square, since it's a square, its opposite sides are going to be parallel. So what does that mean? So if we take line GA as a transversal, then this angle here, EGA, and this angle here, DCG, these are alternate interior angles, right? And since these two sides are parallel, then the alternate interior angles are going to be congruent. Also, as I marked off in green, so angle D and angle F are congruent since they're both right angles, so we can apply the angle-angle postulate for similarity, and we get triangle GDC is going to be similar to triangle BFE. And therefore, we can, using properties of similar triangles, we know that length of GD divided by length of BF equals length of DC divided by length of FE. So we know that length of GD and length of BF are both 1, right? So if we do some algebra and simplify, we get DC over F equals 1, so DC is equal to FE. Now we can use the Pythagorean theorem, so in this right triangle BFE to get EF squared plus 1 squared equals BE squared, and DC squared plus 1 equals CG squared. So if we substitute DC equals FE into these equations over here and we simplify, we end up with BE squared equals CG squared. And if you take the square root of both sides, we get BE equals CG. And we're not going to use negative values because negative lengths don't make sense. So we can throw out the extraneous values. So we also know since triangle AEG is equilateral, then length of side EG is equal to length of side AG. So by the betweenus property of segments, length of EF plus length of FG equals length of AC plus length of CG. So we have this angle here, DCG, which is actually has a vertical angle, right? Angle ACB. So angle ACB and angle DCG are going to be congruent, right? And we know that this angle here, DCG, is congruent to this angle, right? EGA, which we showed earlier. And since triangle AEG is equilateral, angle here for G is going to be congruent to angle A here. So in other words, triangle ABC has two congruent angles, and those angles measure 60 degrees, right? Because we know that measure of angle G is 60, so measure of this angle is 60, and then this is going to be 60 and 60. So if you do this, we know that the sum of the measures of an angle of a triangle is 180 degrees. If we just simplify, we'd get this angle is 60. So long story short is triangle ABC is equilateral. So we know that length of side AC equals length of side BC. So we can go back to this equality we have up here. So EF plus, and since FG is equal to 1, I'm just going to write EF plus 1 equals what? Well, AC we just showed is equal to BC, so I'm going to substitute BC here, plus CG. So what is CG equal to? Well, we know from the Pythagorean theorem, CG is going to be square root of 1 plus CD squared. So, and we also know that EF, right, is equal to CD, right, which we showed earlier. So we can substitute CD for EF, and then we can also substitute the fact. So we know that the length of side BD, which is the side of the square, is 1. So length of BC is going to be equal to 1 minus the length of CD. So if we substitute and simplify, we get 2 times the length of CD equals a square root of 1 plus length of CD squared. And if we simplify, we get length of CD equals square root of 3 over 3. Now we know that length of BC equals 1 minus CD, and we also know that length of AC equals length of BC. So length of AC is going to be equal to 1 minus length of CD, right? Because AC equals BC. So in other words, length of AC equals 1 minus the square root of 3 over 3. Now, if we want to find the length of CG, we just plug in what we know about the length of CD and then into this formula. We get length of CG is equal to 2 times root 3 over 3. So finally, we can find the length of a side of the equilateral triangle. Length of segment AG is equal to length of segment AC plus length of segment CG. So if we substitute what AC is and what a CG is and simplify, we get length of segment AG is going to be 1 plus square root of 3 over 3. So the perimeter of this triangle, since it's equilateral, it's going to be 3 times the length of one side. So in other words, 3 times 1 plus square root of 3 over 3. So if we distribute and simplify, we get the perimeter of the equilateral triangle is 3 plus the square root of 3. Okay, so let's move on to problem 2. So if you see this kind of dashed circle here, and we have a tangent line at point A, and we have these angles that are marked X. And we want to find this question mark here, the measure of angle ABD. So the first thing to notice is that since this line is tangent at point A, then these angles X, 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 X. So 5 times the measure of these angles is equal to 180 degrees, which is a straight line. So if we do a little algebra, we get measure of angle X equals 36 degrees. So if we look at this arc DE, right? So we have angle A here, this angle, angle EAD, right, which is going to be, measured by X, right, is going to be equal to 1/2 times the measure of arc DE, right? That's the property of inscribed angles. So measure of arc DE is equal to 2 times the measure of angle X, right? So we also know that measure of angle X here is equal to 1/2 times the measure of this arc here, right? AE, since the angle is a tangent chord angle, right? So we use the same formula as we do for the inscribed angle. So measure of angle X equals 1/2 times the measure of arc AE. So that measure of arc AE equals 2 times the measure of angle X. Okay, so if we look at, this thing here, this arc AD, we can use the additive property of arcs to get measure of arc AD equals measure of arc AE plus measure of arc ED, and then we can substitute what we just found. So measure of arc AD equals 2 times the measure of angle X plus 2 times the measure of angle X, so it equals 4 times the measure of angle X. So this was the key thing. We want to find out what the measure of this arc AD was. So now if we look at angle ABD, well, that's an inscribed angle, right? And its corresponding arc is the same arc here, right? AD. So we can say measure of angle ABD is equal to 1/2 times the measure of arc AD, because it's an inscribed angle, right? So that's the formula we use. So we can substitute. We know the measure of arc AD equals 4 times the measure of angle X. So 1/2 times 4 times the measure of angle X, and then we're left with measure of angle ABD equals 2 times the measure of angle X. So we know the measure of angle X is actually 36 degrees, right? That's one of the first things we solved. So the measure of angle ABD is equal to 2 times the measure of X, which is 36 degrees. So measure of angle ABD equals 72 degrees. This last problem was kind of tricky, but I enjoyed solving it. So we're given a right triangle ABC and right angle A, and then we have these angle bisectors of the acute angles intersect at point P, and we know the distance from point P to the hypotenuse is square root of 8. So we want to find the distance from point P to point A, or the angle A right here. So this vertex. So first thing we have to know is that the distance from P to the hypotenuse is square root of 8, and we know that square root of 8 is then going to be equal to the length of the segment PQ, where PQ is perpendicular to the hypotenuse, right? That's the definition of distance between a point and a line, right? You do the perpendicular and then you find its length. So, okay, another thing we have to think about is the angle. So if we have like a right triangle, and if we draw these angle bisectors, they actually intersect at a point that's called the incenter of a triangle, and that basically means that point P is going to be the center of an inscribed circle. So it's basically a circle that will fit neatly into this triangle. So it will pass through point Q and then point S and point R, which we're going to later talk about. But that's going to be important because we know that the length of PQ, square root of 8, is actually going to be the radius of this incircle. So what I'm going to do now is I'm going to actually draw segment PR and segment PS, which are, so segment PR is going to be perpendicular to side BA, and segment PS is going to be perpendicular to side AC. So, and these are going to be the other points where the circle passes through. So they're going to measure square root of 8 because they're going to be radii, right, of the circle. So now we have something that solves for length of or the distance from point P to point A, right? Because this thing, this quadrilateral RPSA, right, is going to be a square, right, since it has these right angles, and you know these two things are equal in measure. So length of the diagonal PA is going to be the distance from point P to point A. So we know, since this is like a square, that this is going to be a 45, 45, 90 degree triangle. So length of PA is going to be equal to square root of 2 times square root of 8, which is the length of the side of the square, right? And square root of 2 times square root of 8 is square root of 16, which is equal to 4. So the distance from point P to point A is going to be 4. So I hope you enjoyed watching this video. I really thought that these problems are pretty interesting and fun to solve. They're pretty tricky. They're pretty tough since they're on a math competition. But I hope I explained this well. So feel free to watch it more than once if you don't understand something. And I hope to see you during my next videos. All right, everyone. Have a good night. Bye.